Um, okay, hello everyone. I'm Haimeng from Caltech, and it's my pleasure to be here to share with you this recent work um, establishing exponential quantum advantage in processing massive classical data. And this was a joint work with Alex, Hartmut, Ryan, John, Gerald, and Robert. Um, and I guess to begin with, the overarching question we want to address or try to attack in this work is this seemingly grand question of how will quantum computers impact our daily life eventually. And you might wonder why this would be a question in the first place. And the reason is that if you really look closely to the application space of quantum computers, you start to realize that maybe it it hints at a possible future where quantum computers will only be specialized devices for some niche tasks. And the reason is that conclusive advantage of using quantum computers over classical computers has only been established in a few specialized tasks, such as cryptanalysis or quantum simulation. And the reason behind that was because these problems possess special structures that quantum computers can exploit. But we believe these structures to be hard to exploit by classical computers alone. For example, if you look at factoring or cryptanalysis, the reason was because of some algebraic structure that quantum computers can utilize. And also say for simulating quantum dynamics, these are problems that are inherently quantum in the first place. So we would naturally expect quantum computers to be useful in simulating quantum dynamics. Of course, this would already lead to prospects for advantage in, say, quantum chemistry or condensed matter physics, but arguably, for the majority of the applications that we will see in our everyday life, such structures are very unlikely to appear. In particular, for the majority of the applications that we see, they're about the processing of unstructured massive classical data, where these special fragile structures that can be utilized by quantum computers are probably not there. And so it has been largely unclear whether quantum computers will eventually be useful for delivering general utility with such wide impact in all these fields that we will encounter in our everyday life. And so to understand more closely why it is so hard to get advantage in these unstructured classical data, we could look at a specific example of what a classical task that will look like in our daily life. For example, so imagine that you want to try to figure out a movie to watch tonight. And what you probably do is you will go on a streaming platform and you will select a movie and read a bunch of movie reviews so that you would be able to make an informed decision of what movie you want to watch tonight. And there might be some positive reviews, some negative reviews, and these review tags can be, say, represented by a high-dimensional feature vector, say these X vectors here, and each of them comes with a label labeling whether it's a positive or negative review. And so in order to make an informed decision, you'll likely want to perform the so-called sentiment analysis task, where given a movie review text X, you want to classify it into a positive or negative reviews. And this is like the fundamental task that is behind, say, how Netflix built their fortune on. Like Netflix started with an algorithm for doing, say, movie classification and recommendation. And that's like a prototypical example of what a classical task will look like in our daily life. Let's think a little bit about how would a classical machine learning agent approach this problem. So imagine you are a classical agent and you want to process this data and learn how to classify these movie reviews into positive and negative ones. So what you will do is you'll go onto the website, you will start to read a bunch of these training examples. Say you read the first movie review and you put that into your memory. And then you start to read the next one and put that into your memory, and so on, until you've read the entire data set, or in other words, that is the entire world that is relevant to the task that you are trying to attack. And people often call this phase of data loading phase, where you are trying to load the data that is relevant to your task into your memory. And then with the data loaded into your memory, you can start to process the data and try to analyze this data set in order to distill the useful information from it. And so in the simplest case of classification, such as sentiment analysis task, a classification can be reduced to, say, training a linear model that is basically a hyperplane in a high-dimensional feature space that separates the positive reviews from the negative ones. So in other words, it can be represented by this normal vector W here, which represents the decision boundary of classification. And at the end, what you want to do is that given a new test data point X, you want to predict whether it's a positive or a negative review. So that simply means that you want to predict whether the test vector X stays on this side or the other side of the decision boundary. And in the simplest case of linear classification, that amounts to predict whether the inner product between the test vector X and this normal vector W is positive or negative. So positive would mean that it's a positive review, and negative would mean that it's a negative review. So at the end, it all amounts to predicting this sign of this inner product quantity. And so more formally, one can define such a classification task where you are given these data points and you want to classify new test vectors. And so forgive me for printing such long sentences on a single slide. My purpose here is try to convince you that I'm not hiding any assumptions under the rug, so that all the assumptions that we're making here are explicitly stated on this slide. So more formally, we're defining the classification task as the task where you are given these data points xi and yi randomly sampled from n training examples. And each of them has a d-dimensional sparse feature vector, these xi's, and a label corresponding to that, yi. And the goal is to train a regularized d-dimensional linear classifier W, such that we can predict the label of any classifiable sparse test vectors. So we are making a few assumptions here. The first one is that we are assuming that these feature vectors are sparse. So that means the number of non-zero feature components in these vectors does not grow too fast with the dimension. And this is usually the case in, say, natural language processing or, say, RNA sequencing, because you wouldn't hope that a single review text would contain the entire English vocabulary, for example. So you can think of these features as marking like individual words. And so the number of words that will appear in a single review text is likely to be small rather than spanning the entire English vocabulary. So that's usually the case in, say, natural language processing. And we are also assuming that we are training a regularized classifier. So that means we are making the assumption that we're adding a penalization to the L2 norm of the weight vector W. So it's a usual practice in training linear classifiers where we are making the problem more well-behaved by adding such regularization. So by regularized, we just mean the strength of this regularization is a constant that doesn't change with the dimension of the data. And the last assumption that we are making here is we are assuming the test vectors that we want to classify are classifiable. So by classifiable, we mean that the margin or the distance between the test vector and the decision boundary does not vanish too quickly with the dimension. So in particular, you can, like, for simplicity, you can think of this just as being, say, bounded away from zero. And that is intuitively quite reasonable, because if the margin is too small, that means the test vector is sitting right on top of the decision boundary. So in some sense, it's saying that this test vector is not classifiable in the first place because it doesn't have a clear label associated with it. And so we only aim to classify the test vectors that are classifiable in the first place. So that's the entire set of assumption that we are making here for this classification task. And so the first result that we have is that with the same amount of samples, which is of order n up to polylogarithmic factors, so that means you are going over the entire training examples a few times, a quantum machine of polylog d size can solve this classification task, whereas any classical machine of d to the 0.99 size cannot. And so this 0.99 exponent is kind of arbitrary. In fact, it can be any constant that is strictly less than 1. So it comes from some technical artifact, but in all practical purposes, you can just think of it as linear in D. And so this is saying that any classical machine will basically have to store the entire feature vector in order to solve the task. But there exists a quantum algorithm that can solve the task with only polylogarithmic in D size, which is exponentially smaller than the classical machine. And furthermore, one can think of a slightly harder task that we call dynamic classification, where the training examples changes over time, but the underlying classification rule that we want to learn remains roughly the same. So you can think of this as a scenario where the language habit of the user or their preference for different movies changes over time slightly, but then whether a movie is good or bad, at the end, the label associated with the movie review remains roughly the same. And in this harder case, what we show is that a quantum machine of polylogarithmic size can still solve this harder version of dynamic classification using only order n samples up to polylogarithmic factors, whereas any classical machine that does not have enough exponentially larger size, say it only has d to 0.99 size, it will require at least superpolynomially more samples. So this is saying that in this dynamic version of classification task, if it does not have enough size, you will suffer from you'll suffer from a superpolynomial blowup in your sample complexity as well. So if you are assuming that the samples comes in one at a time, then that will mean there will be a sample and time separation as well. And this result is sort of complementary to the first result in the sense that the first result is saying that if you want to match the performance of the quantum machine with the same amount of samples, you will need to have an exponentially larger size. And the second result is saying that if you don't have enough size, you will need to compensate it with superpolynomially more samples. And a good mental picture to think of these results is in the context of large-scale scientific experiments. So, for example, imagine that you're at CERN working on experiments in the large particle colliders. What is usually the case is that within each run of this experiment, there will be a gigantic volume of data generated from the experiment. And you couldn't hope to store the entire data set into your classical memory. And so what this result is telling you is that if you now have a small quantum chip of polylogarithmic size, then you can keep squeezing all these amount of classical data into this small quantum chip and be able to solve this classification task within only, say, a few rounds of the experiment. However, if you only have classical machine, because the volume of data is so large, and you couldn't hope to store the entire data set into your memory, what will happen is that you wouldn't be able to see the classification rule clearly within any single execution of the experiment. And therefore, you have to repeat the experiment many, many times. And in particular, in this case, you have to repeat it superpolynomially more times until you will be able to see the classification rule. And that will be very expensive and costly to do because even a single run of the experiment is very expensive. And that is the results that we proved for this classification task where we have labels associated with data points. However, in modern practice of data science and machine learning, these labels are usually hard to obtain, or maybe we are just trying to figure out some hidden patterns in the data set that we was not aware of before. And so when we don't have access to these labels, we will have to turn to these kind of unsupervised learning approaches. And one typical example is called dimension reduction, where we are trying to figure out the direction in this data set that explains most of the variance of the data set. And so more formally, one can define such a dimension reduction task as a task where we are given these data points xi, sampled from n training examples randomly, and each of them are still a d-dimensional sparse feature vector, but now we don't have access to the label associated with it. And the goal is to learn an identifiable d-dimensional principal component w, such that we can predict the low dimension representation of any new sparse test vectors. And so principal component just means the direction in the feature space that explains most of the variance of the data set. So more formally, that means it's the eigenvector of your data covariance matrix that has the largest eigenvalue, meaning it explains most of the variance of the data set. And we are making the assumption that this principal component is sort of identifiable. And by that, we mean that, first of all, it's a prominent principal component that explains the amount of variance that is larger, significantly larger than the second most explainable direction. And so that means the eigenvalue that explains is sort of gapped away from the second largest eigenvalue. And moreover, we are assuming that there are some prominent feature that has non-negligible overlap with this principal component. So say in the context of natural language processing, it is often the case that when you only look at the word good or bad, you already roughly know whether a movie review is a positive or a negative review. So in such cases, by looking at this prominent feature, this word good or bad, you already know roughly where the principal component is, but you might still need to know the entire feature space in order to really pinpoint this principal component. And that's usually the case in many applications. And we are also assuming that there exists such a prominent feature here. And if you are familiar with, say, quantum chemistry or condensed matter physics applications where people are trying to prepare the ground state of some Hamiltonians, you'll realize that we are making a similar assumption here. But in the ground state preparation context, people are assuming that you have access to a good enough initial state that has non-negligible overlap with your ground state. And that's essentially the same technical assumptions that we are making here. And the end goal is to predict the low dimension representation of any new sparse test vectors. And this one-dimensional representation just means the projection of this test vector onto this principal component. And we want to estimate that to some, say, constant epsilon error, for example. So this is the formal task of dimension reduction. And what we show is similar results, similar to this classification task that we talked about earlier, albeit using quite different technical tools and quantum algorithms. But the end result is basically the same, where given the same amount of samples, a quantum machine of polylogarithmic size can solve this dimension reduction task, whereas any classical machine would have to be exponentially larger. And we can also consider a dynamic version of this task, where the data set, the training examples, has a distribution that changes over time, but the principal component or the final low dimension representation we want to predict stays roughly the same. And a quantum machine or polylogarithmic size can solve this dynamic version of dimension reduction using only order tilde n samples, whereas any classical machine that is exponentially larger but doesn't have enough size would require at least superpolynomially more samples. So these are the main theoretical results presented in this work. And I'd like to stop a little bit for questions if you have any. And then we'll move on to see a little bit of practical examples for how these main results manifest itself in realistic data sets.
Sorry, I have a basic question. So there are two questions at this stage, right? So how do you get around the data loading problem, right? So, and the second thing is, what is exactly your output? So when you're saying that you're learning something, does this mean you're essentially outputting some expectation value of some observable by doing some sort of repeated sampling or something like that?
Right. That's a great question. So the data loading problem is exactly the problem that we are trying to attack here. And so I will get to that in more details later when I'm explaining the quantum algorithms and how we tackle the data loading problem. And what we are trying to get eventually are, say, in this dimension reduction problem, we will be able, the end goal is to output, say, a single scalar value that is the low dimension representation of this test vector. So in particular, the output will just be a number that is close to the projection of the test vector onto this principal component. And similarly, in the classification example, the output will just be a single binary number, which says whether a test vector is a positive or a negative review. So that's the output of the of this formal task. And in fact, the quantum algorithm that we will introduce later will be able to output some classical model that will be able to predict the label of any test vector that you would like to predict on eventually. But for simplicity, you can just think of the output as a single binary label of the test vector.
Right. Thank you. Looking forward to the algorithm.
Mm-hmm. Okay. So another question that you might have is, maybe I'm hiding a lot of very large constant in these polynomial or other asymptotic notations. And maybe the polynomial has a degree that is so large that maybe these results are not really practical. So we really try to optimize the quantum algorithms, and in particular, how many qubits it will require to run the quantum algorithm. And so we optimize it a lot, and we really tested on these realistic data sets, including, say, movie review sentiment analysis task using data from the Internet Movie Database, or the single-cell RNA sequencing task using some peripheral blood mononuclear cell data set. And we are calculating how much machine size you will need in order to achieve a specific performance requirement. So we are testing the binary classification task and the dimension reduction task here. And for the classification task, the performance metric is simply the accuracy of your classification. And for dimension reduction, the metric is how much variance of the data set you can explain compared to the variance that can be explained by the ground truth principal component. So it represents the quality of the principal component that you can find. And we are plotting here 4 different, or actually 5 different quantum classical algorithms. In particular, this quantum oracle sketching algorithm is the quantum algorithm that I will introduce later. And you can see that as the performance requirements can continue to grow, the machine size required by this quantum algorithm doesn't really change too much, so it stays approximately constant. However, we are also comparing against these classical streaming algorithms that use various different techniques of doing memory saving, and they are sort of optimized for memory efficiency. In particular, we are comparing against a feature hashing method, which randomly put your features into a smaller number of buckets so that the dimension can be reduced. And then train a linear classifier using a streaming method based on that, so that you are optimizing your memory efficiency instead of storing the entire data set first. And a similar technique is called sparse Johnson-Lindenstrauss transformation, which do a random projection of your initial feature vector into a smaller subspace so that the dimension is also smaller than the initial feature dimension. And so as you can see, all these classical streaming algorithms has an exponentially growing machine size as the performance requirement grows. And we are also comparing against the standard classical algorithms based on sparse matrix manipulation and QRAM-based quantum algorithms. All these algorithms proceed by first storing the entire data set, either in a classical memory or in a quantum memory, and that will blow up their machine size because you need to store the entire data set first and then process it. So their memory consumption is much higher than the other methods. And in particular, we are calculating the machine size here. For quantum algorithms, it's calculated by how many logical qubits you are using, plus how many classical scalar registers that you are using. So it's the entire quantum and classical memory you are using throughout the entire training and inference process. And for classical algorithms, that's simply calculating how much scalar number registers you're using. But of course, to translate that into how many qubits, physical qubits, or physical bits that you're using eventually in your machine, that will depend on the implementation and the accuracy you are demanding. So for example, in order to be fault tolerant and error corrected, these logical qubits will have to be, say, compiled into more physical qubits using, say, high rate error correction code that will blow up the memory cost by, say, a factor of 5 or 10. But for the classical algorithms, it will also depend on, say, how you encode a single floating number using, say, 32 bits or 64 bits, depending on the precision you want. So the actual number of bits needed by the classical machines will also be multiplied by 32 or 64, for example. But we are sort of abstract away these implementation details and focusing on the logical level, how much machine size you will need in this plot. And so I guess the overall the result or message here is that the machine size required by the quantum algorithm doesn't really grow as the accuracy requirement grows, but that of the classical algorithms grows exponentially, which is kind of in line with all these scaling law observation of modern machine learning practice. And the same feature appears in all these different data sets where we also tested social media topic analysis and some drug discovery data set where you can also see that the machine size of the classical algorithms blow up exponentially while that of the quantum algorithm stays roughly the same. And in particular, all these quantum algorithms can be actually implemented with less than 60 logical qubits, which is reasonably foreseeable in the near future with all this rapid development in high-rate error correction code and fault tolerance architecture. Yeah, are there any questions?
Clarification, like to do this comparison, do you take the number of data samples to be exactly same?
Right. So the data set is the same data set. So they contain all these training examples in this data set, for example. So the data are given exactly the same.
I see.
Okay. And So I guess these are the main results of the paper, and I hope these main results kind of convince you that machine learning can be a broad domain of exponential quantum advantage, despite all these previous discouraging results on how there are so many obstacles in obtaining advantage in machine learning. And one last thing I want to sort of emphasize about these results is that these exponential quantum advantage are proven unconditionally. So that means these advantage are will persist even if we live in a world where BPP is equal to BQP or P is equal to NP, or even if we grant the classical machine infinite time to compete with the quantum machine. So in such a world where the computational complexity hierarchy collapses, there will be no superpolynomial time advantage for, say, factoring or a quantum simulation, but there will still be this exponential quantum memory advantage that we prove here. And so now I want to switch gear to tell you more about how this advantage is achieved. In particular, I will tell you how this quantum algorithm is developed. And if time permits, I will also tell a little bit about how we prove the classical hardness part. But before that, are there any questions on the main results of the paper? Okay, if not, I guess I will tell you more about the quantum algorithms next. So I'd like to invite you to think a little bit about how you would want to achieve quantum advantage in such a classical task where the input is classical and the output is also classical. So if we look at how a classical machine learning agent approach the problem, it often approaches it by, say, reading individual or querying individual data sample and try to process them one at a time. So imagine you'll be asking a particular user, what do you think of the movie? And the user will tell you a piece of movie review text, and you will process that, and then you will go on to the next user and try to process the next data point. That's how a classical learning agent usually proceed. But now that you have a quantum computer, what you are likely to think is maybe I can just query all these users in quantum superposition, all at the same times, simultaneously. And that is what people usually call a quantum oracle query, because it's not that realistic. However, if you work in this model of quantum oracle query, where you assume the ability to make such query of all these different users in quantum superposition all at the same time, then indeed you can prove exponential speed up over classical algorithms, assuming access to this quantum oracle. However, the problem is that if you really think of this, implementing this in a classical world that we live in, you start to realize that it just seems impossible to do, because how would you possibly be able to query a million different users on Netflix all at the same time in quantum superposition? That just doesn't make any sense. So the entire problem is that we live in an effectively classical world where we don't have access to these classical data in quantum superposition. And how can we still utilize the ability of quantum technology to better process these data? So one can ask this question of how can we access a classical world in quantum superposition? And if we can do that, then we can have all these quantum algorithms that we already know of to utilize these quantum oracle queries and process data in a more efficient way. So this is also the data like what people call the data loading problem in the literature. And so I like to invite you to think a little bit about how you would be able to solve this problem, how you would access classical world in quantum superposition. And there is actually a pretty simple solution that is what people call QRAM. So recall that we have already defined this data loading phase where we are storing the entire world into our memory. And so one first idea that you might have is that now, if I simply upgrade this memory to a quantum memory, or what people call quantum RAM, maybe I can just utilize the ability that I have, like, say, coherent control over this quantum RAM, and be able to create this quantum oracle query that we wanted earlier. And it turns out that that's indeed the case. So if you are storing the entire data set into a quantum memory, then indeed you can use, say, control gates, where you can control on, say, the quantum algorithm state. You will be able to query these classical data stored in this QRAM in quantum superposition. And there are, of course, many different ways of implementing this QRAM, where in some of these implementation, the data are still classical, but the control that you are using to access the data are quantum, so that you can put them into quantum superposition. And in some other implementation, even the substrate you use to store the data are also qubits, and so they can support more flexible quantum queries as well. But the idea is that if you upgrade your memory into a quantum memory, then indeed you can create quantum queries out of it. So if you really create quantum queries from this quantum RAM, then it turns out indeed that you can run these quantum algorithms using these quantum queries, and be able to solve these data processing tasks much faster, say exponentially faster than the classical machine. However, if you really compare the end-to-end complexity of this solution to the classical machine learning algorithm, you see that there's actually no end-to-end large quantum advantage here. And the reason is that the data loading phase is already taking too long time and too much memory. In particular, if you think of this as, say, you're inverting a matrix or doing some other matrix manipulation, assuming that, say, your matrix has dimension n, and say it's sparse, so that the number of non-zero elements is still order n in this matrix, then the data loading time it will take you, say, order n time. And you also need order n space to store the entire matrix. And on the other hand, classical algorithms can do matrix multiplication or matrix inversion or other operations in time n cube. So if you are already paying the data loading time, then you couldn't hope for beyond cubic speed up anymore. And moreover, in the machine size perspective, there's also no advantage because you are storing the entire data set into your memory. And so to make things worse, if you want to maintain a coherent copy of your entire data set, you will likely need to do error correction on your quantum RAM. And so even in the simplest case of error correction, where you have a local decoder, say you would need a classical coprocessor doing error correction sitting next to each of the qubit that you have. Even in the simplest case, you would already have order n classical coprocessors in total. And so you might think that maybe I can just remove all the qubits that I have and run classical learning algorithms on these classical coprocessors. And it turns out that if you repurpose these classical coprocessors meant for quantum error correction to run the classical learning algorithms directly, then you can utilize all kinds of parallel computation techniques, and you will be able to solve the problem much faster using these classical coprocessors alone. So it turns out that there's no place for the quantum bits anymore if you really compare the end-to-end time and space complexity. So in light of that, one can further refine the question and into this following challenge question, where the goal is to access a classical world in quantum superposition, but without the need to store the entire world. Because we've seen if you first store the entire world, then the overhead of maintaining this coherent copy will be so large that you couldn't hope for any advantage over classical algorithms. And so to attack this problem, one can borrow some ideas from classical machine learning literature, where they also have this problem of their data set being so big that they couldn't afford the overhead of storing them all at the same time in their memory. And one idea they developed is that instead of storing the entire data set, you only maintain a model of the data set that you gradually update as the data set comes by, as each data sample comes by individually. So in this linear classification example, the model is simply an estimate of this decision boundary, or this normal vector W. So you start with an initial guess of this normal vector W, and with each data sample coming by, say a movie review comes by, you update your estimate or your model of the data a little bit, and then you just throw away that data set so that you don't have to store it. And then you go to the next data point and you do another update to your model, and so on until you've seen all the data samples. And then you hope that your model will converge to a model that is as good as a final model that you can use to predict the labels of new test vectors. So notice that the point here is that you are processing each individual samples on the fly. So after you process it, you just throw away the data sample and go to the next one, so that you don't have to pay the memory cost to store that sample. And throughout the entire,
sorry for the interruption. Could you maybe briefly comment on how it is related to the streaming model? Because it does sound like streaming, right? Like you're looking at some data and you're throwing it once you've used it.
Yes,
I'm not very familiar, so.
Yeah, so it's very similar to the streaming setting, but there are some technical difference in the sense of how the data are generated. So in the streaming setting, people often allow adversarial ordering of the data samples coming in, but here we are in a more machine learning setting where the data are sort of sampled from an underlying distribution. But up to that technical definition, you can just think of this as a data stream coming in, and you want to process it and figure out some underlying property of the data stream.
Thank you.
Yeah, and the point here is that throughout the entire process, all you store is this model of your data set. You never store the entire data set. And so this idea of processing data on the fly and incrementally update a model of the world that is relevant to your task has all these different names in the classical algorithm literature. For example, sometimes it's called classical streaming algorithms. Sometimes it's called randomized sketching algorithms. Sometimes it's called online learning algorithm in the machine learning literature. But the underlying idea is that you're processing the data on the fly, and you never store the entire data set. And so what we are doing here in the quantum algorithm is something similar, but instead of a classical model, now we have a quantum model that we want to update. So you can just think of this as a quantum state that we are gradually update. And so what we do is that for each data sample coming in, we apply a small quantum rotation to this quantum model. So it will be a nearly identity unitary applied to this initial state. And then we repeat that for all the samples that we have. And the goal of doing that is that we will have a random gate sequence where the randomness comes from the data samples. And we want that random gate sequence to approximate a single query to the quantum oracle that we wanted. And so if we can successfully create a single query to this quantum oracle using this method, then we can just plug this subroutine into any quantum algorithm that make quantum oracle queries and instantiate the oracles in these quantum algorithms and be able to run these quantum algorithms in an end-to-end fashion where the inputs are now classical data samples. At first glance, you might think that this wouldn't work because quantum algorithms has a very much defining feature that is very different from classical algorithms. So in particular, quantum algorithms require coherence to work, but classical algorithms can do whatever randomization they want. So you might think that this procedure will continuously pump the randomness in your data into your quantum machine and eventually lead the quantum machine to decohere. And so you might think that at the end, the output state will just be a completely maximally mixed state that doesn't have any information of the input data. And so it turns out that if you doesn't design the small quantum rotation carefully, that is indeed the case. So the data randomness does lead to decoherence, very severe decoherence, so that there's actually no quantum advantage in general. And you can rigorously analyze this phenomena using tools from randomized Hamiltonian simulation or QDrift, where the idea is quite similar, because in randomized Hamiltonian simulation, you want to assemble or construct the time evolution of some very complex Hamiltonian. And you proceed by randomly sampling individual terms in this very complex Hamiltonians and just do the time evolution of that individual term. And you hope that by doing such a randomized procedure, you would be able to assemble or approximate the time evolution of this complex Hamiltonian. So this is similar here, where we want to assemble the quantum oracle of the entire data set, but we only apply small quantum rotation corresponding to these random data samples that we get. And so the tools can be imported from the randomized Hamiltonian simulation literature. And it turns out that if you choose the step size of individual rotation too large, then indeed it will lead to decoherence, and the output will be just maximally mixed state. But if you choose the rotation time step to be too small, then you will need to consume a lot of data to even get a single quantum query. And compared to classical algorithms, there will be no advantage. So it all boils down to the question of how you would be able to design a carefully designed quantum rotation in order to achieve advantage. So it turns out.
Sorry for the interruption. Yeah, just trying to understand. So what so at least from your picture, it seems very similar to, yeah, as you mentioned, what you do in, say, QDrift or randomized Hamiltonian simulation, where one can show that if your input is random, let's say it's some state from some high random distribution, then you do get some, advantage in simulation, but it's on average, right? In the average case. So is it something? So I'm just trying to connect that to what you're saying, since you've started with this analogy. So can I think of it that way, that you're assuming that your data is from some high random distribution or some specific random distribution, and you are kind of implementing some sort of procedure which in average gives you some advantage?
Idea is, so just a clarification, the randomness here are not the initial state. The randomness is in the classical data that you get, and it turns into randomness in the gate that you apply. So technically it's not hard randomness, but rather say a uniform distribution on the data sample, for example. But the idea is roughly correct in the sense that the average channel of this random gate sequence, by carefully designing the quantum rotations, will approximately implement a quantum oracle. So in some average sense. So in particular, that means the expected channel of this random gate sequence will approximate the unitary oracle that you want to implement. So that's correct.
Okay, thanks.
It turns out that you need to carefully design the rotations. In particular, they had to be nearly orthogonal in order to avoid this decoherence effect. So by that, I mean the Hamiltonian terms associated with each data sample will have to be supported on an orthogonal subspace. And so that will avoid the error from propagating across these individual subspaces and compound in a detrimental way. And so by forcing them to be orthogonal in their own subspace, the error will sort of be contained in their own subspace. And it turns out that the sample complexity for assembling a single query will be brought down by an exponential factor. And turns out that that will suffice for advantage to happen. And it turns out that's also the optimal way of constructing oracles. So at the end, what we show is with order n times q squared samples, we can emulate q quantum queries to an oracle of n items with no memory overhead. And this is the algorithm that we call quantum oracle sketching, because intuitively, this is sort of assembling the oracle or making a rough sketch or approximate sketch of this oracle using these random data samples. And so that might seem,
like, sorry for the interruptions. Like, can you explain the source of the decoherence? Like, I don't understand why we are getting the maximally mixed state if we are only applying unitaries.
Right. So if you are only applying unitaries, the end result will be a pure state. And the pure state will be random, and the randomness will depend on the random gate sequence, which further depends on the random data sample that you get. So on average, the result that you get, because you don't ever sort of remember what data sample you have seen earlier, because you are not storing the data sample, you are processing them on the fly. So effectively, at the end of this random gate sequence, you will be able to see the average of the pure state, where the average is over the randomness in your data sample, rather than this individual pure state if you have already stored the data sample that you've seen so far. So at the end, you can only see this average density matrix, which if you doesn't carefully design the random gate sequence, it will be a maximum mixed state. So the trick here is you need to carefully design it so that each individual pure state that you get are approximately sitting around the target pure state, so that their average is still roughly a pure state. In comparison to the situation where all these pure states are distributed randomly on the Haar measure, and the end will be a maximum mixed state if you average them. So that's what I meant by decoherence.
I understand.
Okay, great. And so that might seem a little bit abstract. So I'd like to give you a concrete example of how this works in the simplest case of building the oracle of a Boolean function. So here, our goal is to estimate some property of a Boolean function with a support size n. However, we don't have access to this oracle or any other query method of this function directly, but rather we only have random classical data samples, xi and f of xi, where, say, for simplicity, we assume these xi's are drawn uniformly random from the support. So what we actually do is, with each data sample coming in, say xi is equal to 1001, and the Boolean function value is equal to 1, we apply a multi-controlled phase gate, where the control pattern exactly matches the input x. And the small rotation, the phase rotation, is proportional to the Boolean function value. And note that this multi-controlled phase gate is supported on log n many qubits rather than order n, because with log n qubits, you already have a Hilbert space of dimension n. And this multi-controlled phase gate can be written as this exponential form, where, say, if the input state is indeed xi, then the projector in the exponent is giving you 1. So you will get this exponential phase applied to this initial state xi. But if the initial state is orthogonal to xi, then the projector will be 0, and exponential of 0 will be identity. So it's doing nothing on the initial state. So this is indeed a multi-control phase gate where the phase is proportional to the Boolean function value, and also some evolution time t that we will specify later. And M0 here is the number of samples you're allocating to implement this single oracle query. And we will also solve for how many samples you will need to assemble an oracle later. And so you just repeat this multi-control phase gate for all the samples that you've seen. And the result is this random gate sequence, which are all commuting with each other. So you can just aggregate them and express them in the basis of X. And so the phase that you get on each individual basis X is going to be proportional to the frequency you see that specific X. And when the number of samples is large, the frequency will approximately be equal to the probability of seeing that X. So now if you choose the evolution time t to be pi times n, you see that the n cancels out with the probability, and the phase that you get is exactly pi times f of x. So that's exactly -1 to the fx power, which is the phase oracle of the Boolean function you want to implement. And so the result is that if you work out the math of how this frequency concentrates around the probability, you will see that with order n divided by epsilon samples, you would be able to implement an epsilon approximate uniter, a uniter that epsilon approximate this phase oracle in diamond distance. And so if you are familiar with the Q-drift literature, you will see that in the usual Q-drift sample complexity, the number of sample will be proportional to the evolution time squared. And the evolution time is order n here. So if you naively apply the Q-drift machinery, you would thought that you need n squared samples to assemble even a single quantum query. And turns out that with order n squared samples, a classical machine can solve everything already. So there would be no advantage. But it turns out that by designing these Hamiltonians to be orthogonal to each other, and in particular here, the Hamiltonians is just the projector onto the subspace X, you can bring down the sample complexity by an exponential factor. And it turns out that this is the optimal way of assembling the oracle, and you will be able to get advantage from it. And using that, you can assemble a single query to the oracle. And now, in order to estimate some property of the function, you will likely you want to run some quantum query algorithms, making, say, in total Q queries. And so you just replace each query by this procedure. And in order to get a final epsilon error, the error budget you have for each query will be epsilon over Q. So the number of samples you need will be n over epsilon over Q. And since you are not storing the samples, you are processing them on the fly, for a different query, you will need to allocate a fresh new set of data samples. So the total number of samples will be Q times the number of samples for each query, and that gives you this advertised NQ squared scaling. And you might be curious, like, where does this quadratic slowdown comes in? Because it seems that the quantum algorithm is sort of extensive in Q, but the number of samples, it turns out, is actually quadratically growing with Q. And turns out that this is the fundamental price you have to pay in order to assemble coherent quantum queries from these incoherent random classical data. And this is the same quadratic scaling as in Born's rule, where amplitude squares to probability, or say in quantum sensing, where Heisenberg limit squares to standard quantum limit. So a good way to think of this is, say, in quantum sensing, when you are trying to sense magnetic field to epsilon accuracy, suppose you have quantum queries to the magnetic field, then Heisenberg limit tells you that you only need Q equal to 1 over epsilon queries. However, if you only have classical data samples, then standard quantum limit tells you that you need 1 over epsilon squared samples. And that's exactly what you get if you plug in n equal to 2 and q equal to 1 over epsilon. N equal to 2 because it's a single qubit problem. And if you plug in the Heisenberg limit 1 over epsilon q, you get the standard quantum limit. And that's also how we prove that this NQ square scaling is essentially optimal by reducing to the distinguishing classical probability distribution, similar to the standard quantum limit proof. And in order to use that for machine learning applications, that's not enough. You have to show that this procedure is robust to the noise and correlation in your data, and it also supports flexible data structures. So beyond Boolean functions, it turns out that you can also use this idea to assemble the block encoding of sparse matrices when you are given random non-zero matrix element of that sparse matrix. And similarly, you can assemble the state preparation unitary of any amplitude encoded vector when you are given random component of that vector. So say in the classification example, this component will say be the label vector, and each time you get a random component of it corresponding to a random training example and their label. And it turns out that this machine learning task has query algorithms that has polylogarithmic machine size and polylogarithmic query number. In particular, that's designed by, say, for linear classification, that's from the linear system solver, and for principal component analysis, that's from quantum ground state preparation algorithms. And so, however, these algorithms are assuming access to the quantum queries, so we need to instantiate these oracles using this quantum oracle sketching idea. So if you plug in the Q into this NQ square scaling, you get this advertised order n up to polylogarithmic factor scaling. And since quantum oracle sketching doesn't incur any memory overhead, the machine size you need stays the same. And so that's how you get the quantum algorithm result, where you can solve this machine learning task with order n samples and polylog d size. However, one last point is that the quantum algorithm gives you a quantum state, amplitude encoding the solution vector. And in order to predict for many test vectors, you still need to read out classical information from this quantum state. But in general, that's difficult because when you measure the quantum state, it will collapse. And likely, you will need to prepare this quantum state many, many times in order to read enough information out of it. However, it turns out that you can design a variant of classical shadow tomography that we call interferometric classical shadow. And it turns out that it will suffice for the purpose of predicting classifiable test vectors and predicted the low dimensional representation of any sparse test vectors. And so what this classical shadow procedure is doing is that it's applying a random Clifford gate and measuring the computational basis. And it will generate a bunch of completely classical information. And you will use that as your final classical model. And this model will just be this descriptions of the Clifford gate and this random bit string measurement outcome. It turns out that the classical model is exponentially more compact than just storing this entire W vector. And particularly only polylogarithmic D many bits suffice to specify this classical shadow model. And so end-to-end, you can think of this procedure as producing exponentially compact classical model out of massive classical data in a way that is only efficiently possible via quantum technology. However, the classical lower bound is saying that if you want to use classical technology alone, it has to use exponentially larger memory.
So can I ask a small question? So once you're using classical shadows, do you have to what is, because I don't remember the state of the art now, but I think initially the computational complexity was quite high, right? Even after you get the shadow to get to the actual observables, is that an issue here, or?
Right. So for here, the computational complexity will be polylogarithmic in N and D. So it will be efficient. The reason is that for the purpose of predicting the label or the low dimensional representation, it turns out that you can, it suffices to predict some low rank observable. So you can reduce those final tasks as the prediction of low rank observables. And for low rank observables, Clifford classical shadow can actually be implemented very efficiently. So it turns out that, and it also comes from the sparsity assumptions and other things. So it turns out that it can be implemented efficiently with these assumptions.
Awesome. Thank you.
Mm-hmm. Right. And you can also sort of see from this numerical simulation that we did on implementing the quantum oracle sketching procedure for all kinds of data structures, that in practice, the number of samples you need is actually quite favorable. So in particular, the constant from the numerical simulation is quite favorable. Like they're all like less than 5, for example. And if you are interested, you're welcome to check out the code and develop further upon that. And so that concludes the quantum algorithm part, where the goal, the message is that we have this new algorithm called quantum oracle sketching that solves the data loading problem. And essentially, it allows you to query the classical world in quantum superposition in a memory efficient way. And so now I'd like to switch gear to tell you more about the classical hardness proof. And the central message there is that one can convert separation in our queryability, namely making classical query versus quantum query, into a memory advantage. But before that, I'd like to stop a little bit more for questions on the quantum algorithm side, if there's any.
So I have a question. So for the so if I consider the block encoding input model, right? So there, could you also have a sketching algorithm that works not just for sparse matrices, but maybe non-sparse matrices? That's not possible, right? It's probably not possible. Because
yeah, that's a great question. So the sketching algorithm actually doesn't rely on these sparsity assumptions that QSVT usually relies on. But in order to do, like, say, block encoding of a non-sparse matrix, you will indeed suffer from an extra normalization factor that will be proportional to, say, the Frobenius norm of the matrix. And I think it is indeed doable to sketch such a subnormalized block encoding, which will be useful for, say, low-rank data processing problem rather than sparse data processing problems.
So whether normalization is the Frobenius norm is what you're saying. So the Kerenidis Prakash data structure tree, that's what with QRAM access, that's what they use to generally get like the Frobenius norm dependence. So you're saying that you can have a sketching algorithm which gives you the same sort of dependence?
Yes, exactly. Yes.
I see.
Yes. Okay, and I guess I will continue to talk a little bit more about the classical hardness proof, but it will be a little bit quick. And so if you want to know more about it, you are welcome to send me an email, or we can discuss later about this. So the major idea or the major steps are, first, we are gonna prove a theorem that connects query separation to memory advantage. And then we'll show that if you doesn't have enough memory, you will have to compensate it by using a lot more samples. And finally, the first two are sort of proved for a Boolean function task. And finally, we need to embed that into these machine learning tasks so that we can say the machine learning tasks are classically hard as well. And so the first result we show is for any query problem that requires Q quantum queries or QC classical queries, there exists an associated learning task where if you want to solve it with the same amount of samples as quantum oracle sketching, which takes like n times q squared samples, any classical machine will have a size at least QC divided by Q squared. So what this means is that if you have any slightly larger than quadratic query separation, for example, if your classical query complexity is order n, but your quantum query complexity is n to the 0.49's power, then if you plug the numbers into this space lower bound, you have the space being at least n to the 0.02's power. But on the other hand, the quantum algorithm usually only uses polylog n qubits. This will give you an exponential memory advantage from any slightly larger than quadratic query separation. In particular, for the machine learning task, we showed that the classical query complexity is actually n to the 0.99's power, which is from some correlation test that we embed into this machine learning task. And the quantum query complexity is polylogarithmic, so that gives you the maximal space lower bound that is advertised earlier. And these results come from a sample space lower bound for classical algorithms, where the number of samples you need, m, times the space you have, s, is at least n times the classical query complexity. And then if you plug in the nq squared sample complexity of quantum oracle sketching, you get this space lower bound of QC divided by Q squared, because the n cancels out. And to understand where does this sample space lower bound comes from, one can view this query problem in a more in a slightly twisted way or more intuitive way. So imagine that you have n different users, and the goal is to rate a single movie. This will correspond to an oracle of n size n support, and the oracle value will be whether the movie is good or bad. So you can think of x as labeling the indices of these users, and f of x will be the opinion of each individual user. So that will be a Boolean function oracle. However, it is often the case that there are a bunch of high quality users, so that by only reading the reviews written by these high quality users, you would already know whether this movie is good or bad. So in some sense, querying these high quality users already suffice to determine the goal. And that is the essence of classical query complexity, where if we only look at these the oracle values of these QC different inputs, we would already be able to determine what is the property of this oracle. And in other words, this is characterizing the amount of information you need to estimate some property of this oracle. However, in reality, we don't get oracle queries, but you only get random data samples from these n users. So this can be think of as more of an oracle property estimation problem rather than a query problem, because we now we don't have query access, we only have random data access. And we need to design a oracle property estimation task so that it's maximally classically hard. So to do that, we deliberately inject noise into the data and form this so-called noisy oracle property estimation task. And we also call it NOP for short. And the way we inject the noise is to invent a different variable that we call alpha that corresponds intuitively to the user's mood that they have today. So the idea is basically the user's reaction of a movie depends on their mood. So when they are happy or sad, their reaction of a movie can change. And their mood fluctuates randomly over time. And we need to gather the feedback of a user in both of their moods, like both in when they are happy and when they are sad, in order to gather an accurate feedback of how these users think of this movie. And more technically, this is saying that the map from the user's happy behavior and the sad behavior to this final reaction, to this assembled reaction of f of x, is given by some low discrepancy encoding. So this just means that when you only look at its happy behavior or the sad behavior, you cannot tell what is the function value f of x. Only when you gather both f1 of x and f2 of x can you figure out what f of x is. And so that takes a long time because these data are randomly sampled. So it's very unlikely that you will hit the same user twice. And hitting the same user twice takes roughly order n time or samples because the data are randomly sampled. So that means the problem of estimating the property of the oracle becomes the problem of communicating between the sad user and the happy users. And such a communication only happens at a time cadence of order n. So only when using order n samples do you get a chance to communicate between the happy users and the sad users. And each time you communicate, all you can bring along is your memory. And that memory has a bounded size S. So the total information you can communicate between the moods is bounded by the number of rounds you can communicate times the number of bits you can communicate each round. And the number of rounds is simply the number of samples you can gather divided by n, because only after n samples you can communicate one round. And each round you communicate s bits. So the total information you communicate is order m divided by n times s. However, the information you need to gather in order to estimate the property is at least QC. So that gives you a chain of inequality, and that gives you the sample space lower bound, where the number of samples times the space is at least n times QC. So the general idea here is just turning this learning problem into a communication problem between your past self and your future self. And at the end, using communication complexity tools, which can be intuitively understood in this way, but technically it's much different. But at the end, you will be able to show this sample space lower bound. And if you plug in the number of samples you need for quantum oracle sketching, you get this classical harness, where the space you need is bounded by classical query complexity divided by quantum query complexity squared. And now we can consider the node problem of correlation, which has the maximal query separation. That will give you the maximal space lower bound for classical algorithms. So that proves a query separation can be turned into a memory advantage.
Hi. So I had a small question in the previous slide. So we essentially needed to query any user twice, right?
Yeah, it'll be like a few times, but yes.
Yeah, like any user needs to be queried once with good mode and once with bad mode, if I'm understanding it correctly.
Yeah.
So, like using the birthday attack, wouldn't it actually take just order root n queries instead of taking order n queries?
Yeah, so yeah, so it kind of depends on the model, because we are sort of forcing when we are deliberately injecting the noise. So we have a specific pattern for the users to change their mood. We will change the mood roughly order n times. So it's not like the randomness is not only coming from the randomness in sampling from the n users. The mood also changes on a time scale of order n. So without going into order n samples, you wouldn't be able to see any user from the other mood. So that's how we control the time scale to be at least order n.
Okay, I see. Yeah. Thank you.
Right, so that proves that in order to solve this node problem, you will need at least order n space. And then we bootstrap it to show that insufficient memory must be compensated by more samples. So for example, for this node task, if it does not have enough memory, the progress you can make on this problem is bounded by a constant. That's what we proved. Then we construct a so-called XOR node where we are asked to solve the node task, solve polylogarithmically many independent instances of this node task simultaneously. And that is realized by asking the algorithm to predict the XOR of the decision bit of all these independent instances. And that will amplify the hardness exponentially with the number of repetitions you have. And so for polylogarithmically many repetitions, the progress you will make if you doesn't have enough memory will be superpolynomially small. And finally, we wrap it into a dynamic version of the node task, where each time the data distribution changes a little bit because you are sampling an independent instance of the XOR node. And so since you can only make superpolynomially a small progress on each individual instance, in order to make a constant progress on the whole task, you will need to repeat it superpolynomially more times. And that means you need, in total, superpolynomially more samples. That's how we bootstrap the first results into the dynamic version. And finally, all these are proved for node tasks of Boolean functions. But we need to prove hardness for machine learning tasks. And we do that first by proving that these machine learning tasks are BQP hard. So that means you can embed any polynomial size quantum circuit into this machine learning task. And then we will embed precisely the quantum oracle sketching circuit for solving the dynamic node task into this machine learning task. And so if you can solve this machine learning task, you will be able to simulate this quantum oracle sketching circuit, which will solve the dynamic node task. But solving dynamic node task classically is hard. So that means the machine learning task itself will be hard as well. So that concludes the classical hardness part. It's a little bit technical, and I'm only speaking on a sort of high level intuition, but the message there is simple, where we show that the separation in our query ability can be converted into a memory advantage. So I hope that these results kind of convince you that a small quantum machine can already process massive classical data and solve large-scale machine learning problems, whereas any classical machine that want to match the performance will need exponentially larger size or superpolynomially more samples. And so we hope these results open the possibility for quantum computers to be broadly useful in our daily life, because these data processing tasks appears in all aspects of our daily life. And one final point I want to make is that this exponential quantum advantage are proven information theoretically. So they rely solely on the correctness of quantum mechanics and independent of any computational complexity assumptions. And if you extrapolate this exponential scaling, you will see that hundreds of logical qubits, given sufficient time, will be able to outperform or overpower any classical machine built using every single atom in the observable universe. But of course, in order to really see that, you would also need a universe scale classical data set and the processing time that is probably comparable to the age of the universe. But in any case, quantum mechanics hasn't really been tested at such a high complexity regime. So because most of the experiments that we do are focused on, say, few body quantum mechanics problem or many body quantum mechanics problem that can be reduced or interpreted in a few body way. So arguably, we hope that through our results, machine learning actually offers a fundamental testbed for quantum mechanics at the so-called complexity frontier, which is what a quantum computer, a fault-tolerant quantum computer, can ultimately allow us to probe. just similar to, say, how large particle colliders enable us to probe or test the standard model at the high energy frontier. And with that, I'd like to thank you for your attention, and I'm happy to take any further questions you might have.